Hey everyone, today we are going to take a look at a application of exponentials which is used commonly in chemistry, and it kind of stems from, or we're going to launch this from a headline that was recently in kind of People's Magazine. So it says a 12-year-old boy finds a 69 million year old fossil on a hike in Canada. And kind of the questions that we might have mathematically are, how did they arrive at that 69 million year old number? And, potentially was it just 70 million? Or, how can we use the information that we have in order to date something that is extremely old? And what does that process look like? So it is, a nice kind of combination of mathematics and chemistry that allow us to do that. And generally what is used, there are a few different strategies, but one of them that's commonly used is called half-lives. So, the skinny on half-lives, as you'll probably learn more about in chemistry, is there are particular isotopes, or chemicals that we would expect to be degrading over time at a particular rate. So if I know that I started with a certain amount of this isotope, and over time I've got, a tenth of it or 5% of it, then I can say to a pretty high degree of accuracy how old that particular fossil or that sample is. So that's what a half-life in general is going to do. So let's kind of take a look at a, contrived example that's very, very easy, and then we can use it to apply or kind of get a formula from, and so on and so forth. So here we have an isotope that has a half-life of 200 years and starts at 8,000 milligrams. After how long will there be 1,000 milligrams left? Well, the important part of this, and kind of one of the bigger takeaways here, is what this point of time looks like. So a half-life of 200 years. So a half-life is the amount of time it takes for a sample to degrade to half its value. So this is going to change depending upon the isotope that you're looking for, but all those same isotopes degrade at the same rate. So, for instance, there's an isotope called carbon-14, which I believe is something like 5,730 years. And every time we see carbon-14, we know that it has that exact same half-life. So that's kind of the key to being able to date some of these things. But in our example, we, start off with 8,000 milligrams, but then every 200 years, we're going to be taking half of that amount. So after 200 years, well, now we've only got 4,000. From there, at 400 years, now we have half of 4,000. And we can see that this kind of looks like our tennis tournament situation here, where we have half of the amount every single time. And let's say, if I looked at this sample and there was 500 milligrams, okay? So if I looked at this sample and I saw 500 milligrams, then I would say, this fossil's 800 years old, because we might have an idea as to how much we started with, and we know its half-life. So what does our exponential equation look like? Well, it's similar to our basic a times b to the x, but with some adjustments. So in this case, the amount that I have left over is going to be equal to our starting value. Our b value is a half, but then our exponent needs to kind of be adjusted, because if I put just a t here, then that would be every year that it's going to be going, cutting in half by, and what I want it to be is every 200 years. So what this actually means is that I need to give my exponent some sort of correction factor. And in this case, that's going to be our half-life. So here, and I'm going to switch this half because I don't want anyone thinking that that is... So we correct by our half-life value here. So now if you take a look at this equation here, if I plugged in t is 200, the first thing that we're going to do is divide by that 200 to get a 1, and then I will apply that half just once, and that's what I want. If I plug 400 into there, then I'm going to divide by 200 and get 2, and that's because it will have halved in value twice. So to answer the question up top, how long will there be 1,000 milligrams left? There's 1,000 milligrams at 600 years. So, we can answer that as we need be, but the important part is really the equation that we came up with here. So this equation could be used in this particular situation. If we take a look at this, so a particular isotope in a fossil that initially started with 100 milligrams in the living specimen now has 12 milligrams. This isotope has a half-life of 5,720 years. So this is pretty common in that we don't know how old this fossil is, and that's what we're trying to figure out. But we do know kind of the amount of isotope that we should have started with and that we ended with. So in this case, I'm going to say, okay, I know I've got 12 milligrams of this isotope started with 100, and this is a half-life equation, so I've got that half, and then this is going to be T divided by 5,720, because that is the half-life of my substance. And now what I have to do is solve this equation for T. So right off the bat, I'm going to look to isolate my exponential. So I'm going to divide both sides by 100. So divide by 100. Now I have 0.12 equals 1/2 t to the 5,720. Just going to rewrite this over here. And I might just switch this to 0.5 instead of that half, and that's just going to be kind of for when I convert to a logarithm. So this is t divided by 5,720. In this case, I want to log base 0.5 on both sides. So similar to our last lesson, if we had e to this, then we would do the natural log of both sides. But here the base that I'm going to be doing is a 0.5. This is the same step as converting to a logarithm, so whichever method you have more comfortability with, feel free to use that one. And then this left-hand side is just a number, so I'm going to type that in and see what we get. So log 0.12. So here I'm getting, on my left-hand side, 3.058 equals t divided by 5,720. And then I'm going to multiply by 5,720 on both sides. So we've figured out that this fossil is 17,496.87 years old. So we can see that, we end up with a pretty accurate number. Not too much of this is kind of rounded or anything like that, or unrealistic. This is all pretty standard. So here we actually end up with our formal half-life equation. All right, and it's not unlike a times b to the x. Our b value is a half our y and a really are pretty much unchanged. The only adjustment that we have here is in our exponent we divide by the half-life. So I'm going to do a few more examples, and then there is a worksheet to kind of accompany this. And the thing that we're going to be solving for might be different kind of every time. For instance, here, we know the half-life, we know the sample that we have, and we're curious as to how much remains. So in this situation, be mindful of kind of what information you're provided with and what you're looking for. So here I know this. I'm going to actually plug these values in because we know the 22,860. So I plugged in everything here. I almost didn't even create a modeling equation because the thing that I'm solving for is on the left-hand side. But T represents, how long has this been decaying, and then the value underneath, the H, is my half-life, so that's 5,715. What's interesting about this is after you simplify that exponent even just a little, and maybe I'll switch this to just 0.5 right here and try to keep that going forward. So 22,860 divided by 5,715. I get an exponent of just 4. And again, what this is demonstrating is that this will have reduced by a half 4 times in that period of time, because every 5,715 years we are reducing by half of its value. And if this has been going on for 22,860, then that's kind of 4 cycles of that. So, we could probably do this in our head, but I've just got the calculator here anyway. So we end up with the final amount that we're left over being, looks like 5 milligrams when I punch that into my calculator. I was saying we also know that we could have just done this out 4 times, because that is kind of what our half-life is referencing, is how long does it take to get to 5 milligrams. This one happened to work out super conveniently, so don't anticipate that always happening. Example 3 is another good case of, what information that we have versus what we don't have. So I might just write the parts of this that are really, really clear that we know about. And this A naught, or A sub 0, is, again, it's a label for saying, well, okay, how much should we start with versus how much was our final amount, which is always on the left-hand side. So I should have kind of highlighted that earlier. I am going to call this 0.5 because it's easier to deal with. Has a half-life, so we're not going to know this. And then this is 45,310. So this one definitely takes a while to decay. And the part of this that's a little bit tricky is if 10% of the isotope exists. So it almost doesn't matter what we're starting with here. We can choose what we're starting with, so long as what we end with is 10% of that. And there's a few different tricks, but generally I would say, let's pretend that we just started with 100 milligrams or 100 anything. Then after that, we're only going to have 10% of it. So this is kind of 10% of 100. And the reason why that's not going to matter is because our first step here is actually going to be to divide both sides by 100. And you're always going to get that same percentage when we do that. So our first step here in solving for t is, I'm going to divide both sides by 100. And then we get 0.10, and that's our 10%. So if you're more comfortable or knowledgeable about this, you can just put that percentage on the left and not worry about the starting amount. I generally just say, okay, I'm going to assume I started with 100 and then just put my percentage as a whole number on the left-hand side. So now I've got 0.5 t 45,310. In order to solve this, I'm going to take log base 5 of both sides, or log base 0.5. So log 0.5, and then this is 0.10 equals t divided by 45,310. So I'm going to calculate that left-hand side. So I end up getting 3.321 equals t divided by 45,310, and then I'm going to multiply both sides by that number. So then we have that this sample is 150,000 years old. Here we can see, that over 3 iterations of that have kind of occurred in that time span. So it's been halved 3.321 times. And yeah, so this is kind of what we're using. So the sheet that you have is a pretty good mix of science and mathematics. So be mindful of the fact, what is a half-life? A half-life is the amount of time it takes for a sample to degrade to half its value. So there's some easier questions and some trickier questions on that worksheet. But yeah, see how it goes, and then we'll bring that in on Thursday. Thanks.